All right, continuing section 5.1, which was talking about simulations and probability. Got an example here. That's kind of a silly example, but which of the following outcomes is more likely when flipping 20 coins? So heads, tails, heads, tails, heads, heads, tails, heads, tails, tails, heads, 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 tails, 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 or all heads. Um, and I don't, we haven't really talked about how to calculate these probabilities or why they are, but basically any sequence of heads and tails is equally likely of any other sequence of heads and tails. So these are all the same. All the same amount of likeliness or whatever, they're all, each of these are, I should say, equally likely, sorry. Now, if we were to look at it from a different perspective, if you said, what's the probability that you flip, actually, this should be 10 times 2, sorry, that you flip 10 coins and you get 10 heads. Well, that's certainly less than if you flip the probability of flipping 10 coins and getting 5 heads and 5 tails. 10 heads is much less likely than getting 5 heads and 5 tails. But the reason is because there's a lot of different ways that you can get 5 heads and 5 tails, whereas there's only one way to get all heads. So this is one way to get 5 heads and 5 tails. You could also get heads, tails, heads, tails. But any one combination is equally likely from any other combination. The law of averages or gambler's folly. The law of averages actually almost sounds correct, but these are both not real things. They're both mistakes. I like gambler's folly. It makes it sound gives you a little hint that it's not right. Some people wrongly believe that if a chance process turns up a single outcome several times, the probability of a different outcome will somehow increase. For example, we're flipping a coin and we get a heads, and then we get another heads, and another heads, and another heads, and another heads. And if I ask you what's the probability that that next one's a head, you're going to say, well, geez, we just got 5 heads. We're due for a tail. So you might think that the probability that the next one is a tail might somehow be better than 50%, which is not true. The coin doesn't know that it came up heads 5 times and somehow that it needs to balance things out by showing up as the tails. It's a random process. Playing roulette, and you observe black has come up 3 times in a row. Therefore, you bet big on red on the next one because the law of averages states that red is more likely to come up next. Nope, equally likely. Probability, the roulette doesn't have memory. Family has 4 kids and all of them are girls. They figure they'll have one more kid and will probably get a boy because the probability of getting all girls and 4 is very small. This is true. The probability of getting all 4 girls and 4 kids is actually very small. But after you've had a girl, 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 and a girl, the probability that next one's a girl is that's going to be 50-50, of course. So that's the law of averages. In baseball, sometimes I don't know if anyone actually says it, but I can imagine an announcer saying that this person is due. They've gotten out 5 times in a row, therefore they're due. And perhaps, maybe they are. Maybe the probabilities that a baseball batter gets on base does perhaps change after they've gotten out a few times. But if it's a true random process, then the probabilities should be the same. These are all incorrect. These things do not have memory. The probability of any given trial does not change depending on the first. There are some things that the probability will change. We'll talk about that later. Example, not another boy. Couple has 5 kids. They're all boys. In an attempt to finally get a girl, they decide to have a 6th. What's the probability their 6th child is another boy? 50%. 0.5. 1/2. Please don't ask me which of these is right or which one of these do I want. I don't care. They're all the exact same number. Simulations. So the imitation of chance behavior based on a model that accurately reflects the situation is called a simulation. Basically, whenever we use a model, coins, cards, computers, to imitate chance behavior in the real world, that's called a simulation. We do it so we can repeat it fast. Simulations are useful in situations where the probability theory is either too complex to handle or where our intuition may fail us. Those are kind of the 2 places that simulations really help. So here's an example of a situation where probability theory is too complex to handle. I thought this was an interesting article. Joe DiMaggio's hitting streak. There was an interesting discussion of the hot hand in the article in the New York Times, written by a couple guys. In the article, the authors claim that one of the most remarkable streaks in baseball history was Joe DiMaggio's 26-game consecutive hitting streak. He basically got hit in 26 consecutive games, which is a record and one that a lot of people say will never be broken. So they're claiming that that was actually not very remarkable at all. Obviously, it is extremely unlikely for any particular individual to have a hitting streak this long, but when you consider all of the players across the 100+ years of baseball, 30 teams, 10 players per team, we're talking a lot of games. We should expect some very unusual performances every now and then. To investigate, they simulated the performances of every baseball player in every season a total of 10,000 times. So they looked at every baseball player, probably looked at their batting average times at the plate, and they simulated 162 games a year for all 30 teams and every single player for all of the years. And they did that 10,000 times. So this is a really, really complex simulation. In each of those 10,000 simulated histories of baseball, they recorded the longest hitting streak, the longest number of games that a person got a consecutive hit. 42% of the trials in the simulation, someone had a hitting streak that was at least 56 games in a row or more. So that's a little less than half, but certainly tells you that you would, that's not that crazy. The longest had been an amazing 109 games in a row. That's almost double Joe DiMaggio's record, which is pretty amazing. But that only happened one time in 10,000. Performing a simulation. Now, we've never really done the state, plan, do, conclude. However, I would maybe recommend you kind of adopting it a little bit for simulations. If I ask you to perform a simulation, tell me, state what the problem's about. What are you trying to simulate? What are you trying to estimate? What do you want to do? Plan. Describe how you're going to use a chance device to imitate one repetition of the process. Detail here. You really need to have enough detail so that someone can read your plan and replicate it exactly. And then also, this is one that people forget this all the time, quite often. Tell me what you're going to record at the end of all of this. Here, they recorded the longest hitting streak throughout the years. So what are you going to record at the end? And then actually do the simulations. 100 repetitions, 1,000 repetitions, 10,000 repetitions. And then use the results of your simulation to address the question of interest that you asked up here. You don't have to use the 4-step plan, but I would encourage you to. All right, so we didn't really even get to this example in class, but I'm going to walk through it for a couple minutes. And we did not get to this one, and although I would like to do it, I don't see us coming back and spending the time to do it in class. So there's a couple simulations in your homework that you can practice on, of course. All right, so here's an example that's kind of worked for us. I'm just going to walk us through it. At their annual picnic, 18 students in the mathematics and statistics departments at a university decided to play a game of softball. 12 of the 18 students are math and 6 are stat majors. So we got 12 math people and 6 stat people. So you can't have a math team and a stat team, not enough stat kids. To divide the teams of 9, one of the professors put all of the names of the students into a hat and drew out 9 players to form one team, with the remaining 9 players forming the other team. The players were surprised when one team was made up entirely of math people. Is it possible that the names weren't adequately mixed in the bag, or could this have happened by chance? Design and carry out a simulation. So I don't think I like the wording of this, actually. Is it possible that the names weren't adequately mixed? Well, sure, it's possible, right? And could this have happened by chance? Well, we can answer that. We don't need a simulation to answer that. Of course, it's possible that it happened by chance. I think it's a better question to say, is it likely that the names weren't adequately mixed? And or I guess, well, you see what you get my point, hopefully. So what we're wondering is how likely is this? And if it's really, really unlikely, then we'll kind of assume that maybe the names weren't adequately mixed and that it didn't just happen by chance, right? So here's the process. State, how likely is it that one team will have 9 math majors given the teams were randomly selected? How likely is it? Basically, what's the probability of getting 9 math guys on a team? That's the probability I want to estimate, right? How likely is it? Plan. Write math on 12 equally sized note cards and stat on 6. That simulates the proportion of people that were math and stat. Thoroughly shuffle the deck of cards and put 9 cards into one pile. Count and record the number of math cards in that pile of 9. This represents the number of math players on that team. So that's what I'm going to record. I don't like that I didn't say record. Record the number of math on team 1. Okay? So do. The simulation was repeated 100 times. I used the computer because I was not going to do this by hand. And I could have done a lot more, but I just did it 100. And I recorded the number of math people on that one team. So we were wondering what the probability of getting 9 math guys on that team is. Well, that happened one time. But it actually happened more than that, because you can get 9 math guys on a team if team 1 has 9 math, right? But remember, there were only 6 stat kids. So if team 1 had 6 stat kids, that would be all of the stat kids. That means it would be 6 stat kids and 3 math, right? Then the other team, team 2, would actually have 9 math kids. So this is a probability that I get 9 on team 1. This is actually the probability, or the number of times that I got, or excuse me, yeah, so I'm sorry. So if the first team had 3 math kids, that means they had 6 stat kids, therefore there would be. So these two outcomes here combine to tell us that this happened twice out of 100. So conclude. We got 9 math students in 2 of the 100 repetitions, 1 on team 1 and 1 on team 2. So our estimate for the probability is 2%. So there's only a 2% chance that this would happen by random chance, assuming they mix the bag up well. Because this value is very small, it's therefore unlikely that it happened by random chance. So we would conclude that the professors did not use a fair random drawing, or the professors didn't mix well. Now, they might have mixed well, right? I mean, it happens 2% of the time. But chances are they maybe didn't mix them up well enough, okay? This has been an interesting example. If you want to practice or play around with it, feel free to, but I don't know if we're going to do it, and I don't know if we're going to do it in class.